So last time we introduced the definition of Artinel series. I indicated the proof of the Chebotauro density theorem. And what I'd like to do today, or in this lecture, is talk about applications of Artinel series. And perhaps this is the first theme. And the second theme, I would like to say a few words about future interactions of classical theory. Now, the most impressive application of Artinel series that was outlined last time was the Chebotauro density theorem. So we proved the Chebotauro density theorem last time. So what does this say? It says that if capital K over little k is a finite Galois extension with group G, and C is a conjugacy class of G, then the number of prime ideals Now remember, the Artin symbol was only defined for unramified P, so P should be unramified. P unramified. And the Artin symbol is equal to class E. Remember, the Artin symbol was defined as the conjugacy class of sigma script P, where script P is a prime ideal lying above German P. This quantity is asymptotic to the density given by the number of elements in the conjugacy class divided by the number of elements in the group times x over log x, as x tends to infinity. It's an amazing theorem. Yes?
Norm P is norm P.
Oh, norm P, thank you, yeah, thank you. Norm P, absolute norm of P less than or equal to x. Thank you. Yeah, so we're counting all the prime ideals whose norm is less than x, whose Artin symbol is the given conjugacy class, and this is what you end up getting. Of course, in the trivial case, so case 1, so examples. One, if little k equals capital K equals Q, then this is just the prime number theorem. This is the prime number theorem. Okay, so this generalizes the classic prime number theorem. 2, if little k is Q, and capital K is the M cyclotonic field, so zeta M is the root of M through the unity, 2 by I divided by M. Oops. That's the M cyclotonic field. Then we know that this is a Galois extension, so capital Q is zeta M over Q is Galois, and the Galois group is isomorphic to coprime residue classes modulo M. And the Galois action can be given as follows. So for each residue class A coprime to M, I will define an element sigma sub A. We define sigma sub A, and all I do is tell you what sigma sub A does to the M through unity, because that by extension tells me what it wants to do in the field. This is simply zeta M power A. This is the action of Galois on the field. Okay, so these are your elements of the Galois group, and the Artin symbol. So for prime P, for P coprime to M. Now the only primes that ramify in the cyclotron field are primes dividing M. So if you take those guys away from the picture, then I'd like to know what the Artin symbol sigma sub P is. That sigma sub P is exactly equal to sigma sub A, where P is congruent to A mod M. So P lands in a, depends only on the arithmetic progression that P belongs to modulo M. So sigma, so it's bad notation, but I think it's, maybe I should have called this tau sub A. Yeah, maybe put tau sub A so we don't confuse people. Then this is just simply tau sub A. Is that okay? So that's better notation. So these the Galois automorphism. Now remember, in the case of an abelian extension, the Artin symbol is actually a group element. It's not the conjugacy classes are single in a sense, right? So you get this. So therefore, if I'm trying to figure out how often is the Artin symbol equal to a particular tau sub A, that's Dirichlet's theorem in primes and progressions. So the Chebotarev density theorem is here. The celebrated. So let's celebrate Dirichlet's theorem here. Celebrated theorem of Dirichlet of infinitude primes and progressions. Celebrated theorem of Dirichlet. The infinitude of primes in parallel progressions. So, hopefully there are more consequences, and this is something that I think Artin probably thought about. It gave rise to his famous Artin-Kruger root conjecture. So he asked himself, well, can we come up with some more examples like this? And I want to illustrate in this talk a bunch of them. That's the applications of Artin. Okay, so we can look at example number 3, which would be the Artin-Kruger root conjecture. Artin-Kruger root conjecture, which basically says that, I'm going to state it for the number 2, but you can state a general conjecture. I don't want to get into the nitty-gritty of the general conjecture. So the question is, how many primes P are there less than x such that 2 is a primitive root mod P? How many primes are there? The 2 is a primitive root mod P. And Artin actually asked himself this question and gave a heuristic argument to say that there's a positive density of such primes, assuming various things. We'll talk about that heuristic argument in a second, but essentially his motivation or his plan of attack was the Chebotarev density theorem. A little bit more complicated example than this is let E be an elliptic curve. Defined, let's say, with rational numbers. And for each prime P, not dividing what's called the conductor of E. Let's not worry about that. It's just a finite bunch of prime, finite number of prime. Ends up being the conductor of E. For each prime P, let E of Fp be the group of points, modulo P. Points of E, modulo P. In other words, if I look at the elliptic curve over the finite field of P elements, then it's again, you look at this thing, and then you can ask, how often is this group a cyclic group? How many primes are there? How many primes P less than X are there such that E of Ft is cyclic? You may ask, why would I care about this? Well, this is actually a question that was initiated by Lang, who I suppose from algebraic considerations was thinking that there should be elliptic analogs of classical theorems. So if you're looking for two generating the residue classes modulo P, essentially this is a question about the multiplicative group scheme, you know. So we can now move to this group scheme, which is an elliptic curve, and ask how often is it cyclic generated by a particular global rational point. But that's the second part of Lang-Trotter conjecture. I won't go into that at all. That can also be attacked by the Chiltern speaker. We'll talk about that. We won't talk about that here. If you want to pursue that, you can look at some of my earlier papers. Number 5 is a little bit more down to earth. So for one, is very clear. It's an elementary. It falls into the domain as a question. It falls into the domain of elementary number theory, but of course the answer does not. In some sense, it's still an unsolved problem. Number 2 requires you to know something about elliptic curve. But this question now is very, very naive and very classical. So let tau n be the Ramanujan tau function. So what is this? Well, it's defined as you take the power series that you would get by taking the infinite product. So take this infinite product as a series of Q, expand it, and it starts off with n equals 1, infinity, and the coefficient of Q to the n is denoted as tau. That's Ramanujan's function. And Ramanujan made some beautiful conjectures regarding this function, and these conjectures have been proved. Of course, there are other mysteries at the top which we still don't know about. But let me ask you 2 basic questions. First question 1. Well, maybe I'll just leave it to 1 question instead of trying to do more things. Given a prime L, how many primes are there? L divides tau. How many primes are there? P less than x, and L actually divides the value of the tau function. So here are three questions, very interesting questions, very down to earth. I want to show you that the Chebotaur density theorem has things to say about all three questions. The Chebotaur density theorem is unable to answer question number 3 there, the first one, about the Gruen conjecture. I'll explain to you why it's unable to do that, although it provides you a very compelling argument with the answers of there's a positive density of such primes. Conjecture number 2 has been answered in the affirmative in the case that E is has complex multiplication. That was part of my PhD thesis. And when E does not have complex multiplication, we have shown that there are infinitely many such primes, and that's a paper that I wrote with Rajiv Gupta in the 1990s. The case of the complex multiplication can be handled by Chebotaur density theorem. The case when E does not have complex multiplication can be handled conjecturally using it's again a kind of scenario that was number 1. For this last question about the tau function, this actually can be answered unconditionally. And it turns out it's roughly 1 over L, the number of primes for which, so tau of P behaves like a random number. The density of primes is like 1 over L times the number of primes. Okay, so these are interesting things that come out of the Chebotaur density theorem. Now, before I move in this direction, let me say a few words about our analysis of the Chebotaur density theorem. In the last talk, I indicated how using the Brouwer induction theorem and combined with properties of Artinel series, you could show the Chebotaur density theorem using non-vanishing properties. So one might be inclined to think that you really need the theory of Artinel series in order to prove Chebotaur density theorem. But that's not completely necessary. And I want to show you a simple group theoretic trick, which might be instructive from the standpoint of it's probably understandable by all of you, which will allow us to just use the Artin reciprocity law alone and not talk about non-abelian null series. Okay. The idea is the following. So some elementary group theory. And this may have, in my mind at least, it has some value in the sense that it's not a bad idea to keep on thinking about things from different angles. So let G be a finite group. Let C be a conjugate sequence. And let G sub C be an element in the class. Let's fix it. So fix a G sub C in the class. Define a function phi. Let's let H be the group generated by G sub C. Cyclic. Hence, H is cyclic. And define phi of H to be equal to 1 if H equals G sub C and 0 otherwise. So it just picks out G sub C. Okay, this function. phi is a class function of H. And remember last time I told you that if I have a class function of a subgroup, I can induce and get a class function of the big group. So we can ask ourselves, what is induction H to G of phi? What is that? I'd like to calculate it. So it's kind of like an elementary group theory exercise. And it's actually pretty simple. In general, so this has nothing to do with this particular choice of H. In general, so this is a general remark. In general, if H is a subgroup, and the xi's were, remember these xi's were coset representatives, coset reps of H and G, then we define that the induction H to G of phi of an element X is equal to the summation over these coset representatives phi dot of xi inverse x xi. This is our definition of induction. This is phi dot being just a trivial extension of phi, basically as if it's in the group, it's the phi value. If it's not, it's 0. That's a trivial extension of the group, so it's phi dot. Now, it doesn't take much thought. If I have an element H in capital H, and xi's are coset representatives, then clearly xi H are also coset representatives. I have one set of coset representatives, and I say fix an element H, and I just do this. Clearly, they're also going to be left coset representatives. So this is the same, you can see as 1 over H of phi dot of H inverse, let's do xi H inverse x xi H. Oops, there's a summation. This down. Summation I, and then phi dot of xi H inverse x xi H. Okay, so we agreed that for any fixed H, this is still a cosine. So we're getting the same thing, and I get H times that I divide by 1 over H. But now, as H runs through elements of capital H, and I run through the coset representative, this runs through all the elements of the group, because the group can be written as a disjoint union of the cosets. So this is nothing but. So this is another way to think of induction. If you like. But I find it, I have to usually derive this after this one, because this is easier for me to remember than this, because I never know how much, what you're dividing by. You see, this is a very unnatural formula, because you're dividing by the number of elements of the subgroup that you've got. Anyway, whatever is strikes your fancy, this is good enough. So this is a general remark for any. So with this remark in place, let me now go back and calculate what is this? Well, this is equal to, in this particular choice of phi, what is it? Well, 1 over H summation phi dot, so G. So I will try to evaluate this at X. This is equal to G inverse X G. Fair enough, everybody? Okay, so let's try to analyze what this is. Let me just now rub this off. We're done with this. But what is this guy? It's equal to 0 unless G inverse xg is G sub c. So G and G. And we need to have G inverse xg to equal G sub c. In other words, it's the x has to be conjugate to G sub c. Right? X has to be over H. G x equals G sub c, G inverse 1. In other words, this doesn't survive. This is going to be 0 unless x is conjugate to G sub c. In capital G, right? Now, the index function is a class function. Depends only on the conjugacy class that x belongs to. So this forces that x, because x has to be in the conjugacy class of GC, in order to calculate this quantity, it's okay if I pick x equal to G sub c. Which means that I look at elements G that commute with G sub c. That is the cardinality of the centralizer of G sub c. Okay, so this is equal to, it's equal to 0 if x is not in the conjugacy class C. And if x is in the conjugacy class C, then it's equal to the order of H, 1 over the order of H times the number of elements in the centralizer in G of G sub C, right? This is the notation I think normally used, centralizer in G of that. Okay. Now, your elementary group theory tells you that the number of elements in the conjugacy class is the index of the centralizer. Right? The number of elements, right? The number of elements of the conjugacy class is the index of the centralizer. Therefore, I could write this as, zero. Index H to G of phi of x equals 0 if x is not in the class, and equal to, well, the cardinality of G divided by the cardinality of C times 1 over the cardinality of H. X is. In other words, I can write this whole mess as, i.e., induction from H to G of phi x is nothing but the characteristic function of the conjugacy class. So this is the characteristic function of the conjugacy class, which is 1 if the class of x is in C and 0, right, of C, times this fudge factor. Therefore, this affords, maybe I have to stay on this board, this allows us to prove the Chebotarev density theorem without appealing to non-abelian L series. Okay, so let's try to see how this works. Thus, but of course I need to use the invariance of the Artin L series under induction. I don't need to use the Brouwer induction theorem. I mean, in the last lecture, it looked as if I was using the Brouwer induction theorem, and I told you how to prove the Artin induction theorem, which by elementary methods, in order to convince you that the Brouwer induction theorem is a reasonable expectation. But now, I just want to drop that whole use of those theorems. So what we will see is delta. So what we'd like to, so the Chebotaur density theorem is asking us to count primes P whose norm is less than or equal to X, whose Artin symbol is equal to the class C. This is what we want to count. So this guy can be rewritten as norm P less than or equal to X, and use delta sub C of sigma P, because sigma P, it's abusive notation. I hope you see. When I write sigma P, I really mean sigma script P for sigma script P, which lies above that. Okay, it's not small abusive notation. Don't worry about it. So you get something like this, and now I can rewrite that as the cardinality of C times the cardinality of G divided by the cardinality of G times the cardinality of H times the induction. So it's norm P less than X, induction H to G, H being that cyclic group generated by the GC. GC was that element I chose, right? Phi of sigma P. Okay. Now, we saw that the point is, I guess you could either use, you could write down induction H to G. That's it. So we can think of it this way. Basically, the formal properties remember I gave you those functorial properties that if you have characters chi1 plus chi2, the L function is ls chi1 plus chi2 is just ls chi1 times ls chi2. So those are just formal properties of, so I'm just going to use those formal properties and say this guy now is the same as the L function of capital K over K sub H by the invariance under induction. So the invariance under induction, I told you, really doesn't use any heavy-duty group theory. It just uses two ingredients. One, to know what the definition of the induction is, and two, how do primes decompose as you move up the various levels. So I just leave that. I told you that was rather easy to figure this out. So this is what we have: ls phi k over kh. Now, what is phi? Phi is the characteristic function of g sub c, and phi is a characteristic function of g sub c corresponding to this abelian extension. Remember what H was. H is the group generated by that group element g sub c. Okay. Therefore, this is an abelian extension, and I'm asking for how many prime ideals are there whose Artin symbol is exactly g sub c. And because, again, of the functoriality of the Artin symbol, that is, I take the Artin symbol was defined here, and then when I restrict to that, it's just a restriction of the Galois automorphism. So under that functorial property, this is nothing but, here, this sum is mod C over mod G times cardinality of H times, now I can write this, I'm asking how many times is this sigma P equal to GC? Well, that we know, in the abelian case, it's just this. Times, this is a character sum over size, and then we have norm P X symbol, of course, restricted to this field, which I'm not going to write down, belongs, is equal to, okay, let's write it down. Restricted to K sub H equals G sub C 1. This is an abelian extension. K over K sub H is an abelian extension. I'm asking how many prime ideals there are such that R is this. It's 1 over the density of this expression. The density is 1 over the order of the H, and therefore you get the Chebotarev density. So let me just write that. From the abelian using the uniform distribution of prime ideals. For the abelian extension. What do we get? We get that this is equal to mod C over mod G times H times, what is this whole expression here? This whole expression here is 1 over H times, so this is 1 over H times, so this is an asymptotic x over log x. As x goes to. So this H cancels here with these two, and you get the right density. This is actually a proof essentially due to Dori, and if you look at Lang very carefully, he tries to say that, but he doesn't give this character theory version. He gives you some small different variation of it. If you like, you can look at it. But that's essentially it. So there's really no need to use Brouwer induction theorem in this process, or the Artin induction theorem. All right, so that after that interlude, let me now get back to this point here. The most important idea in this particular theorem is that this asymptotic is only as x goes to infinity. In other words, we have the fields are all fixed, the groups fixed, the conjugacy class fixed, and this is as x is tending to infinity. What we'd like to have is a description of this theorem. Perhaps I would like to let my fields go to infinity in terms of degree. How does this thing behave? So there are many, many parameters. So, I mean, this is pretty clear from the definition of the Artin L function. It depends on the complex number S. It depends on the extension capital K over little k, right? And it depends on the representation. So with these parameters in place, you'd like to know how does this whole thing behave with respect to any of these parameters, and perhaps maybe one should strive for a better statement of this theorem which takes into account all those things. And this is where essentially analytic number theory enters the picture. When you have several parameters, I'd like to know how the error, so I'd like to know what this error is and how does it behave in terms of these field variants, okay? So we need to know about the error term. We need to know about the error term for many applications in number theory. I mean, I haven't even scratched the surface of what are wonderful things you can do with Chebotarev. I mean, these are three of my favorite things, but there are more than that, right? For many applications. First point, so first remark, goes back to Gauss. First remark. The prime number theorem is often stated as pi of x is the number of primes, p less than x, and that this is asymptotic to x over log x as x goes to infinity. However, Gauss pointed out that you should really be using the logarithmic integral. So this is the logarithmic integral. dt over dt. Of course, if you integrate by parts, you'll start getting an asymptotic expansion that goes like x over log x plus x over log x squared maybe, plus dot, 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 some other expansions you could do. Keep on integrate by parts. So you can see that this approximation to pi of x as opposed to this is probably better, because if you had used this, you may be forced to put an error term of x over log x squared. So this is where the question, when the question of error terms invokes the question of how did you express the main term. Okay. So the Riemann hypothesis is equivalent to the statement that pi of x is actually the logarithmic integral Ix plus the error term x to the half log x. So this is not totally trivial to prove. If you perhaps look at my problems in analytic number theory book, it's there. But that's the point. The point is, if I use the logarithmic integral, I can write this error term down. But if I use x over log x, I can't write this error term down. It'll be O of x over log x squared. I don't want to do that. So this is why this logarithmic integral is an important aspect of this theory. Right. Now, that's first remark. And therefore, in the Chebotarev density theorem, we do the same thing. So pi sub c of x, which is the number of prime ideals, whose norm is less than x. Now keep in mind, this ramification business will always take unramified primes, whose Artin symbol is equal to c. This quantity is equal to cardinality of divided by cardinality of g times Ix plus O of x to the half log x, where the constant now, implied constant, depends on the field. Implied constant. One can actually write this down. Okay, so one, I mean this, sorry, on the Riemann hypothesis. So, yeah, modulo, sorry about that, modulo GRH and Artin holomorphic conjecture, Artin conjecture. So remember Artin's conjecture says the non-abelian L series are entire functions. That's Artin's conjecture. So if you have the function is entire, you can bring in classical analytic number theory and start estimating things in this, as one does with theories of L functions, and crank out the best error term, and this is what you get. However, this problem here is that the constant here, implied constants, are depend on the field. Okay, you don't have my American Journal of Math paper with you, do you? I should have brought it. But anyway, I'll do. I mean, for the purpose of this lecture, I don't think I really need all the details, but I'll indicate this. Yeah. Do you have it in your office? Or you may have it in your bag, right? Well, no, it's okay. I know it's okay. Because, as I said, people are meeting this thing for the first time, so maybe you don't need the finer. I'll just give the reference that you go look at my American Journal paper for the finer details. I might be off by a fudge factors, but essentially this is the idea. So, so if we assume, if you assume this actually, so this was worked out in a paper by myself, the American Journal of Math, modular forms and Chebotarev density theorem. So assuming the Artin conjecture and the generalized Riemann hypothesis, we found an explicit error term. Explicit error term. With involving the field constants. So that means we tell you how it depends on the field. Before this work, Lagarius and Rudlisco obtained similar results, but not as good error terms, because they only assumed GRH, assuming only GRH. Obtained weaker estimates. I mean, the half is still there, of course, but the field constant, the game on the field constants is the big deal. Obtained weaker estimates. So once you assume, as we saw last time, the poles of the Artin L series, if any, are contained in the zeros of the Riemann-Zeta function. Therefore, you could use that to get the x to the half. But then, how do these field constants that go in here depend? And for that, if you don't have the full Artin conjecture, you get worse estimates. So that was the idea of this particular paper, and of course, applications to various problems. Now, let me just go back to this in order to get myself. When did I start?
47 minutes ago.
Oh, okay, so halfway through. Okay, that's good. So let me kind of tell you at least how perhaps Artin thought about these things, which motivated his formulation of this conjecture. All right, so his idea is the following. So before we continue, maybe notice that with the Chebotarev density theorem, if I have a finite Galois extension group G, then the density of prime ideals P would split completely in capital K is, of course, 1 over the degree of the 1 over the size of the Galois, or 1 over the degree. So this is now. So keep that kind of in the back of your mind. So if I'd like to know how often 2 is a primitive root modulo P, what do we have? By Fermat's little theorem, two of the P minus 1 is always a common root 1 modulo P. That, okay, and we'd like to have, so 2 to the P minus 1 is common to 1 mod P, and we'd like 2 to have the full order for it to be a generator. Therefore, we want 2 is a primitive root mod P, if and only if, for all prime divisors P minus 1. for all prime divisors, just p minus 1. 2 to the p minus 1, so q is prime. 2 to the p minus 1 is not common. So this is, you don't want it to have smaller order, you want it to have that order. So for each prime divisor, if it has a smaller order, it's got to be, you must have knocked off a prime somewhere. Right, so this is what this happens. Now, from the fact that q divides p minus 1, that's tantamount to saying that p is congruent to 1 mod q, which means p splits completely in the q-single common field. Okay? So, recall, q dividing p minus 1 p is congruent to 1 q. That happens if and only if p splits completely in q zeta q. So, for each prime p which splits completely in this field, we don't want 2 to the p minus 1 over q congruent to 1 mod q. So if p, if p is congruent to 1 mod q, and 2 to the p minus 1 over q is congruent to 1 mod p, then by what's called Euler's criterion, elementary number theory, Euler's criterion, tells you that the equation x to the q congruent to mod p has a solution. Right? I mean, this is what's called Euler's. When is 2 a qth power? It's a qth power if and only if 2 to the p minus 1 over q is gone. This is Euler's criterion. Okay? Has a solution. In other words, let's have a look at the fields. So we have q zeta q, and then we have q sort of 2. This is not a Galois extension. The Galois closure is this field. So this is the splitting field of the polynomial x to the q minus 2, right? So this is the splitting field. And the Galois group, sadly, is not an abelian group. So it's a non-abelian group. And the fact that p is congruent to 1 mod q and this thing has a solution means that if p splits completely in this Galois expression. So p congruent to 1 mod q and x to the q congruent to 2 mod p has a solution. If and only if p splits completely in that field. Now, so if we want 2 to be a primitive root, we don't want this to happen for every q. So 2 is a primitive root. Thus, 2 is a primitive root on p. Given where we have p does not split completely. the field Q. Now this field, the degree is 5Q, which is Q minus 1 Q's prime, right? The degree here is Q minus 1. And the degree here is, of course, Q, therefore the degree of this whole thing is Q minus 1. And so the probability, by Chebatarov, the probability that P splits completely is 1 over Q times Q minus 1. And so the probability that it doesn't split completely for every Q is 1 over Q minus 1 for every prime Q. This is the probability that it doesn't split. We want this to happen for all Q. So we expect the density of primes P less than X, the density of primes sets of P for which 2 is a primitive root, should be this. So this is the conjecture. I mean, all this is very heuristic argument, but it's a very solid probabilistic reasoning, right? The probability that something happens is this. You don't want it to happen at every Q, expecting all these things are independent, which they are. Then you end up getting like this. And so you expect that to be the density of prime. So that's a positive number. Because all these numbers are, right? It's a convergent series. And this was Artin's motivation for making this conjecture. Okay? Now, of course, he knew probably, and maybe others did too, that this heuristic reasoning cannot be justified unless you have some knowledge of these error terms in this. Unfortunately, the best error terms are obtained by the Riemann hypothesis. And so the question of whether or not this can be turned into a valid proof, you know, he made it in the early 1930s or 1928 or something like that. And only in 1967 did all the details get worked out, and that was by Cooley. Cooley showed GRH implies Artin proof. Now there are cases where, by the way, the group is nice, in which the assumption of the Artin holomorphic conjecture is superfluous. This is one of those cases. So you don't really need to assume Artin holomorphic conjecture because they're actually holomorphic in this case. I'm using monomial theory and whatnot. So in this case, you don't need to throw in the Artin holomorphic conjecture because the extensions are pretty reasonable. And so this is what we managed to do in using this actually idea and trying to make all these error terms in the splitting count precise. Now, of course, this is theorem that Rajiv and I have. So as defined by Heath-Brown, that 1 of 2, 3, 5 is a primitive root. P influence phenomenon. Now the interesting thing about this proof is our approach initially, and in fact all approaches, used sieve theory. And I still don't understand the role of the sieve in problem and its relation to the Riemann process. So it's a very interesting phenomenon. Somehow the sieve sometimes can be used to replace the Riemann process. Sometimes. This is one of those cases. I mean, but of course it's a kind of convoluted argument to get to that stage. And it's the same argument that we used on the cyclicity of E of Fp for elliptic curve E without complex multiplication. That helps your understanding. Okay, now let me say a few words about these other two problems that I talked about, and then try to devote some time to the future of classical theory. So E is an elliptic curve. Over the rationals. How many primes P that's the next argument such that goes without saying I'm looking at primes of good reduction, so don't worry about that. Such that E of Fp is cyclic. Now, interestingly enough, this actually, you have to ask yourself, what's the structure of an abelian group? So by basic structure theory, finite abelian groups, let's just keep it abelian groups. We know that every abelian group is a direct product of cyclic groups. Okay? Every abelian group is isomorphic to a direct product of cyclic. Now, so you give me an abelian group, and it's isomorphic to the direct product of the Celos subgroups. The Celos subgroups. Now, each Celos subgroup, A sub P is a P group, and you know that the P group, which is abelian, can also be decomposed as a direct product of cyclic groups. And the only way this guy can be cyclic is if each AP is actually cyclic. So A is cyclic if and only if AP is cyclic for every P. A is cyclic if and only if AP is cyclic for all P. If you don't mind, I'm going to change the letter P to L. This is the innovation of 20th century mathematics. L is now also prime. Right? L has been introduced for. Okay. AL is cyclic for every L. Now, AL, as you know, being an abelian group of L power order, will be isomorphic to some direct sum of Z mod L to the alpha I Groups of order L to the I, right? They'll be isomorphic to something like this. So the only way AL can be cyclic is if there's only one component here. Because if there are two components, two cyclic components here, it won't be cyclic. So in other words, A is cyclic if and only if A does not contain an LL group, that is a group of order, cyclic group of order L plus a cyclic group of order L is going to be sitting inside. So there are two components in these LL for all L.
Does not.
Does not, yeah. Does not. Thank you. So maybe I should say A is not cyclic. Okay, well. It shouldn't contain an L. Okay, so now I go back to this problem. Of when is EFP cyclic? EFP cyclic if and only if all L EFP does, sorry for this character remnants from the last talk, it looks like. EFP does not contain an element, right? So now I want to ask myself, for each prime L, I have to ensure that EFP does not have a group of this type, Z mod L plus Z mod L. Okay. So now, so basic abelian, finite abelian group theory. Asking, so what am I doing? I am trying to understand the problem. What does it mean in terms of some criterion? See, it's always this. Every time you have a problem, you have to kind of understand the problem, reformulate the problem in other ways so that you can perhaps use other telescopes to solve the problem, other methods of attack. So I'm doing that. And now the question is, when, for prime L, when do we have EFP containing an LL group? Firstly, when do we, so we don't want that to happen, but now you have to ask yourself, when does it happen? And here is now where you have to do something with elliptic curves, right? You have to bring in the theory of elliptic curves and ask yourself, what's going on here? And instead, you know, in the study of elliptic curves, just as in the classical case, elliptic curves can be studied over various fields. Classically, elliptic curves, the study of elliptic curves started with elliptic curves over complex numbers. Then we moved to over algebraic number fields or function fields and so forth. But then modern 20th century started studying things over finite fields. And when you study certain things over finite fields, it's convenient to look at the algebraic closure. And remember that last time I mentioned that the Galois group Fp bar over Fp is a procyclic group. This means these are cyclic groups generated by the Frobenius. Frobs of P, or if you like to call it. And therefore, the fixed points of the Frobenius is the collection of points of over Fp. Okay. And when I look at the L torsion points, L torsion points of E of Fp bar, the L torsion points, that is those points which are killed by L is isomorphic to two copies of C mod L. This is analogous to what happens over the complex numbers. Complex numbers, you have this division, the elliptic curve of complex numbers, and you know that you have what are called division points on the elliptic curve. There's an addition law, with a Abelian group, and one can talk about L torsion points on the elliptic curve. If you look at the circle, the L torsion points on the circle, it's one of the most basic group schemes, right? So you look at the L torsion points on the circle, those are roots of unity. Now you start seeing, cyclotomic theory, maybe L division points, elliptic curves. Maybe there's an analogy here, and that's correct. That intuition is correct. So anyway, you have this over FP bar. You have this. So if it contains the L group, it means that the Frobenius had fixed that. Okay? So if the Frobenius is fixing that, this is slightly harder to predict. Requires a little bit more maturity, in the sense of not age, but in the sense that I'm assuming a little background on elliptic curves. So we have E of Q bar. So you have a group of points on the elliptic curve with coordinates, algebraic numbers. And inside, you can talk about the L division points. So points killed by L. So this is a collection of points in X in E of Q bar. And it's an additive law. Okay, so L acting on X is 0. So L torsion points. And there are L squared of them, just like here. There are L squared such points on the elliptic curve. And just like we adjoin the L root of unity and talk about cyclotomic fields, it makes sense perhaps to discuss the fields obtained by adjoining L division points on the elliptic curve and try and study these fields as analogs of cyclotomic fields. And the first person who studied these fields, especially in the case of non-CM elliptic curves, is Serre. In a famous paper in 1972, he analyzed the Galois group of this thing and showed that for L large, I think bigger than some, I forgot exactly, but some function of the conductor of the elliptic curve, L large, he showed that the Galois group, so it's called as GL, this Galois extension, GL, is isomorphic to GL2 FL. So if I had the L roots of unity, the Galois group is FL star, which is GL1 FL. So here, by the way, E has no complex multiplication. So let's not worry about the CM business and no CM. I'll talk about this issue later. So if E has no complex multiplication, the Galois group of this extension is isomorphic to GL2 FL. And the size of this group, I think all of you know, is roughly L4, right? And therefore, invertible matrices over. So how many, you know this is an interesting thing. How many elements are there in GL2FL? Okay, let's just try and answer that question right now. Well, those are 2 by 2 invertible matrices over the field of L elements, right? And so I shouldn't pick the 0 vector. So I have L minus 1 choices for the first column, right? L squared. L squared minus 1 choices for the first column, because there are L squared vectors that I can put in here, but I shouldn't put the zero vector, otherwise it's singular. So once having picked that, I shouldn't pick a scalar multiple of that. So the other guy is L squared minus L. Right? I shouldn't pick the scalar multiple of that kind. So this is the size of this group. So as you can see, it's roughly L to the 4. Roughly. We know exactly what it means. Therefore, it seems reasonable. Now, go back and ask yourself, when is it the case that E of FP then contains LL? If and only if the Frobenius automorphism acts trivially. Remember, the Artin symbol is the Frobenius automorphism. Acts trivially on the L division points. It has to act trivially. Well, if the Artin symbol acts trivially, it means that it splits completely in this extension. I.e., if and only if P splits completely in QEL. See this beautiful transporter beam, I call it. You go from one universe to another through reinterpretation. It's a transporter beam. Okay, so you take in the problem, try to understand it, and then moved it into the Chebotarev world by saying, whatever you don't want to happen, it contains an LL group if and only if it splits completely in this field. Now, by Sayre's theorem, this is a Galois extension of that degree. Therefore, the probability that P splits completely in this field is roughly 1 over L to the 4. So you expect, you don't want this to happen, so you expect the density of primes P, such that E of FP is cyclic, it should be equal to product, should be equal P over all L's. Not quite all L's, I'll just put a dash there for a second. 1 over whatever this thing is, L squared minus 1, L squared minus L. Now remember, I said Sayre's theorem is that the Galois group is this for L large. So there is some issue with the smaller L's, and one has to worry about those. Okay. Let's not worry about them now, because there's not the time and place for that. But you can now see how the cyclicity question of E of FP is now translated into not splitting completely in these extensions. And that's how Chebotarev comes into the picture. So this is actually originally a kind of thinking that Lang and Trotter formulated a thing called Lang-Trotter structures. This is the kind of reasoning. Of course, just heuristic reasoning based on Chebotarev language. But now, if you want to prove this, you have to worry about error terms in the Chebotarev density theorem. And you have to do an inclusion-exclusion sieving procedure in this whole game. Okay, now, interestingly enough, if E has complex multiplication, the Galois group was kind of known to Artin and other people. And it's not quite abelian, but it's non-abelian, but it's a little simpler to handle. And there you had basically how I solved this question without, in the CM case, I used this dictionary to move it to the imaginary quadratic field where the curve has CM by. And then there used what's called the Balbiri-Vinogradoff theorem in sieve theory to answer this question using Ray class fields and things like that, where I could avoid the use of the Riemann equation. Sieving seems to do this sometimes. It depends. I don't exactly, can't formulate a precise philosophy of this thing, but in many ways there's a good rationale for that. So how much more time do I have? 15 minutes?
It's 1 hour 20 minutes.
20 minutes? Okay, okay. Then I can chit-chat a little bit about the future of class field theory. Oh, I didn't answer this last question, the tau function. Okay, let me say a few words about that. All right. Details, of course, of all, well, not all, say, but at least the tau function thing can be found in this paper. So now the tau function thing is an amazing thing itself. And this is, of course, the chapter on how the Chebotarev density theorem comes into the picture has to do with one of the fundamental discoveries of 20th century algebraic geometry. Okay. So given a Hecke eigenform, now here I'm going to assume that you know something about modular forms, and if you don't, I strongly urge you to run to Math Science and buy a copy of Problems in the Theory of Modular Forms. Okay. So given a Hecke eigenform, normalized, with, let's keep integer coefficients, with z coefficients. Although the theorem is true in general. Given such a form, let us write the Fourier expansion eigen-Cusp form, normalized Cusp form. So its Fourier expansion starts from 1. Given such a theorem, there exists an analytic representation. So here, as I said, in the world of mathematics of the 20th century, people started looking at representations over other fields. The whole business of looking at p-adic fields was a big deal. And one of the important aspects of 20th century mathematics. So there's an analytic representation, rho sub L, from Galois Q bar over Q into GL2 of the L-adic integers, such that trace of rho sub L of the Frobenius automorphism. See now, here I gave you the definition of Frobenius automorphism for finite Galois extensions, but one can push the limit, you know, take a limit and define a Frobenius automorphism in the limit as well. Okay, so let's not worry about that for a second, because I'm going to move to the finite cases anyway right now. Equals a sub p of a sub p. Okay. It actually equals that for all p not dividing L and level n. So it comes on gamma out of n or something. There's a level of the modular form. You have to remove those primes, and you have this wonderful theorem. What it says is, in other words, this means for each prime L, there exists a Galois extension, KL over Q finite Galois extension. Such that trace sigma p. Now I'm using sigma p as the arc symbol corresponding to this Galois extension. And one knows the size due to some work of Ribbett. KLs have been studied. And essentially, they're essentially some sort of GL2 FL extensions. And, similar to that situation. Okay, so what does all this have to do with the tau function? Well, the Ramanujan tau function is a Cusp form of weight 12 level 1. And so, are you running out of ink? Okay. So it's a Cusp form of weight 12 of level 1. And I can apply this theorem to that particular class form. And it says that tau of P trace rho L of sigma P is congruent to tau of P modulo L. Okay. And we know that that the Galois group, so let's see, so the Galois group is essentially, I'm just going to put a dot there because it's not quite 100% right, but I'll explore this right. Essentially, GL2 FL, isomorphic to almost. So let me the determinant of, so let's just, let me be precise. For L large, isomorphic to set of all elements in GL2FL such that the determinant of gamma is an 11th power, or 11th power. So let's not worry about the second condition. So if Artin symbol, it belongs to this group. So then I start counting how many elements are there of trace 0. Okay, so the rho L embeds this thing, right? So I count how many elements are there of trace 0 in this group. That's how often tau of P is going to be 0 modulo L. So I need to bring this is actually a theorem of this whole business. And it's a consequence of his proof of the May conjectures. So it's not a trivial matter whatsoever. So this is serious stuff, comes out of the May conjectures, and when we use it in this sense to analyze how often a prime will divide tau of P can be translated into a Cherepanov condition. How many conjugacy classes are there here whose trace is 0? I mean, so it's not just one single conjugate. There could be several conjugacy classes, but we have to count all of them. And when you count them and divide by the order of the group, it turns out to be roughly 1 over L. I forgot exactly what the density is, but it's roughly 1 over L density. So the probability for L large, I'm not saying it's exactly 1 over L, but it behaves like 1 over L. And I think in one of my papers, you can find the exact density. So that tells you something about how these Chebotarev densities, how Artin series, how error terms of all these, of this theorem matter. And clearly there's a lot more work to be done in the study of these things. Right. Because in some cases we've managed to get, in these two problems there was this Riemann hypothesis. In this problem, you don't need to have the Riemann hypothesis. Just you're only asking for a single L. But if you're trying to answer the question how often tau of P is 0, well, if it's 0, it's going to be 0 modulo L for lots of prime L. Then you may want to vary L. And then having error terms matters. So, as you know, this famous conjecture of Lamer that says that tau of P is never 0. So at least this whole mechanism and error terms in Chebotarev will give you some knowledge about how often tau of P can be 0. That if it does happen, it's very rare. That's one of the things that comes out of Riemann hypothesis. Okay, so now in the time remaining, let me say a few words about future directions. So the Kronecker-Weber theorem tells us every abelian extension is contained in some simplifying field. For something. And we can ask, are there other theorems, are there similar theorems for an arbitrary number field? Well, we know from the reciprocity law and the work there that every abelian extension of any number field K, every abelian extension of number field K is contained in some Ray class field. But is it possible to describe these Ray class fields as explicitly as we have done in the cyclotomic case? Is it possible to describe to give an explicit description? Of these Ray class fields. And this is what's called Hilbert's fault problem. So in 1900, Hilbert gave a list of 23 problems, and this is still open along with the Riemann hypothesis. So now, interestingly enough, this has an explicit answer in one case, which is very classical. It goes back to Kronecker, Weber, Takagi, and various other people. Kronecker, Weber, Takagi. Let K be an imaginary quadratic. K be an imaginary quadratic. I need to make some definitions, so I'll do that right now. This again now connects itself with the theory of elliptic curves. Elliptic curves over complex numbers, actually. So let O sub K be the ring of integers. So as you know, that the ring of integers can be written as tau. Tau is in the field. So all the integers can be written as linear combinations of tau. So it's every integer is A plus B tau, right? So let's call this, so for each such thing, we'll define the Weierstrass P function. Okay, not 0, 1 over z minus omega squared. Weierstrass P function. It's a doubly periodic function. The periods 1 and tau. Familiar in this theory is called G260 times summation 1 over omega to the 4. Well, if you know, essentially the Isaac time series with 4, thought of the function of tau. And then you have G3, 140, summation omega in K, 0 again, 6. Get these numbers, G2 and G3. Then we define delta, which is not unrelated to the Ramanujan cusp form, but anyway, we don't want to say that there's a relation to that. G2 cubed minus 27 squared. And we will define this function f of z. F of z to be equal to G2 cubed p of z squared divided by delta if G3 is 0, which can happen. By the way, these things can happen only in the so-called complex multiplication case, but let's not worry about that now. G3p of z cubed divided by delta if G2 is 0. So these are special cases, but in general, is defined as G2, G3, p of z divided by delta otherwise. We have this funny function f of z. So I just want to try to tell you that there's an analog of the Kronecker-Weber theorem for an imaginary quadratic field, but it's not so simple and clean and neat as you thought it might be. You have to take this now. I need to invoke some special knowledge on your part about the j function. J of tau is E4 cubed tau divided by delta of tau, where E4 cubed is this modular form, E4 rather is this modular form, 1 minus, I forgot, it's 240 something, summation sigma 3 of m, either to y or z, and go in front, going to infinity. Modular form with weight 4, and delta is the usual cusp form of Ramanujan that I wrote down at the very beginning. Q product 1 minus q of the n 24, where q is equal to either 2 pi r tau. So take this, all these definitions into consideration. And now I have all the functions. I think the theorem is every abelian extension of K is contained in K of J of tau f of 1 over n for some natural number. So that's what you need. You need the j function, and you need this funny construction of the p function. And you take the nth division, as it were, you know, like the nth root of unity type of thing. And so this is something I think Hilbert kind of knew at the time when he was formulating his problem. And so he was asking for what are the functions that we are supposed to be looking at in order to have clean theorems of this type. And even to this day, I don't think the verdict is out. People are still unclear as to what one should do. But in the 1970s, Stark formulated conjectures, which are worth reading, in a series of papers, 1 to 4. And I think by the time he reached the last paper, he was making the conjecture that abelian extensions